Hello, students. This is your calculus teacher, Mr. Allen, and today we are going to finish up chapter 4, integration, and we're going to look at inverse trigonometric functions, and we're going to be integrating. The objectives today are for us to integrate functions whose antiderivatives involve inverse trig functions, as the name implies. We're going to look at an example of where we're going to use something called completing the square to integrate a function. And finally, I just want to review the basic integration rules of all of the elementary functions for calculus. So if we go back to chapter 2 on derivatives, which we kind of skipped, you may recall that the derivative of the arcsine function is 1 over the square root of 1 minus x squared, where the derivative of the arc cosine is just the negative of that. So it's the same result, but it's just negative. So when listing the antiderivatives that correspond with each of these inverse trig functions, you really only need to remember one, and then the other one will just be the negative of it. It is conventional to use arcsine as the antiderivative of 1 over the square root of 1 minus x squared rather than negative arc cosine x. So here are the 3 basic rules that we're going to focus on. And again, if you know, well, let's just go with this. So there's the integral of, so if we go back to chapter 2, if I asked you what is the derivative of arcsine, you would give me something that looks like this, but now we're going backwards because we're talking about anti-differentiation. So we've got the arcsine when we have the square root of a squared minus u squared in the denominator. If there's no square root and it's just a squared plus u squared, that's going to be the arctan plus c. And then, of course, if we have the square root, notice that this is the variable term like x here, like x squared, where here it's a constant squared minus the variable term squared. And I guess you should also maybe notice that there's a x on the outside there. Remember, all these formulas are in terms of u because we use u substitution quite a bit. So for example, if I asked you what is the integral of dx over the square root of 4 minus x squared, well, you should automatically think of that 4 minus x squared as 2 squared minus x squared. This is the a value squared. This is the u value squared. So this is going to be the arcsine. This is going to be the arcsine. And sorry, I'm trying to make that clean. There we go. It's going to be the arcsine, and then we got to do the u divided by a. So that's x over 2 plus c. All right, so here's another one. This one's going to involve arctan, but we're going to have to do a little bit of work here. So notice that our constant here is 2. So when we got to think of something squared that gives you 2, well, that'd be root 2. And then we got to think of this as something squared. Well, that'd be 3x squared. Now notice that we have this 1/3 and this 3 on the top. So where did those come from? Well, that comes from the u substitution. That comes from the u substitution. So then our final answer here is going to be 1 over 3 radical 2 arctan of 3x over root 2 plus c. So this is not a very difficult problem, but if you definitely want to practice it some to make sure you understand how those rules work. And finally, let's look at one more. Again, we're going to do a little bit of u substitution. So we did arcsine, we did arctangent, so you can probably guess what this one is. Notice here that we've got the u term here, the a term here, which is the opposite of what we had in the first problem. And also notice that we have an x on the outside here. So u is going to have to be this 2x, and a is going to be 3. So since u is 2x, then du is going to be 2 dx. And since we didn't have a 2, that's where that extra 2 comes from. So our final answer here is going to be 1/3 arcsecant absolute value of 2x over 3 plus c. All right, let's talk a little bit about completing the square. So completing the square is something that we first introduced to students in Algebra 1 and particularly in Algebra 2. And basically, what you're trying to do is you want to massage your quadratic expression into a way where it's a difference of two squares. So the rule basically is something like this. So like if I had x squared plus 6x, minus 7, let's say, and I wanted to complete the square, you look at this 6. You say, what's half of 6? Well, it's 3. What's 3 squared? That's 9. So what I want to do to complete this square is I'm going to plus 9. Now, if I plus 9 here, I have to minus 9 out here. So then this could be rewritten as x plus 3 squared minus 16. I think I actually said that somewhat incorrectly. We want this to be a perfect square trinomial. Perfect square trinomial. Perfect square trinomial. I think I said a difference of squares, and that's not correct, so I apologize. Anyways, here's a formula for you to kind of remember how to do this. This works out nicely, particularly when the leading coefficient of the x squared term is 1. So let's see how an example of that might look. So we're going to need to complete the square with the denominator here. So the key value to look at here is this minus 4. So that minus 4, what's half of minus 4? Well, that's going to be 2. And what's squared? That's 4. So that's where this 4 comes from. Now, if I plus 4 here, I've got a minus 4 right there. Did I do that right on the last one? Okay, good. So anyways, we've got to balance it out. Notice that I kicked this 7 out here. This is a perfect square trinomial, which means that it can be factored to the quantity x minus 2 squared, and then of course negative 4 plus 7 is 3. Now, if you're not sure if you did this whole process correctly, all you got to do is just FOIL this back out. FOIL it back out, which is going to be x squared minus 4x plus 4, and then you get a plus 3, and you will see that that is indeed what we have there, which is x squared minus 4x plus 7. So this now has been rewritten with, in this case, the sum of squares. So let me go ahead and erase what I have here. So this is the u now, and this is the a. So what will u be? Well, u is going to be x minus 2, and a is going to be equal to the square root of 3. Because remember, we got to take a squared, so it's going to be the square root of 3. So now we can see from the complete square form that u is x minus 2 and a is the square root of 3. In other words, our integral will convert to the following. That looks very similar to the arctangent rule, which it is. So final answer here is 1 over root 3 arctan x minus 2 over root 3 plus c. I also might note here, if you got a square root in the denominator, you do not need to rationalize that. You do not need to change 1 over the square root of 3 to the square root of 3 over 3. That is completely not necessary in this course. You can just leave it as it is. Okay, finally, I want to just review some of the basic integration rules. So the first basic integration rule is the constant multiplier. So if you have a constant k inside of an integral, you can pull it out. 2, if you have this, if you're going to integrate a sum, it's going to be the sum of the integrals. 3, if you're going to integrate just du, it's going to just be u plus c. In other words, it's a linear function. 4, this is probably the most important one. This is our power rule for integration. It's just the opposite of the derivative rule, power rule. This one is also another important one. This is in 1 over u, so that's our natural log absolute value of u plus c. E to the u. This one's a hard one to remember. I'm going to kind of skip over number 7. That's when you're doing an exponential with a base not of e. Of course, you know sine already, cosine, the rest of these. So this is kind of the focus for today, are these guys here. But don't forget, for example, that the integral of secant squared is tangent u plus c. And we studied these in our last section. This one, and this one, when we were doing natural logarithms. So my final example today is comparing integration problems. So look at these three problems. They are very similar. Each one involves x squared minus 1. They're all fractions. So some of these things we can do using the basic rules. Some of these we can't. Let's see how that works out. Let's look at that first. What's that first one kind of look like? That looks like a rule we did today, doesn't that look like something we did today? It sure is. That is, in this case, remember, u here would be x and a would be 1. So that is simply the arc secant absolute value of x plus c. Second one requires a little bit more work, but we can do it. And I'd like you to think about how that works, how that came about. So basically, this is involving some u substitution, and we get a final answer of the square root of x squared minus 1 plus c. So this definitely takes some work. I would be doing u sub on this problem here. So basically, hopefully you recognize that the derivative of this is close to that. So that's a u sub problem. And then our third and final one. This one is actually one that we cannot integrate using the techniques that we've studied thus far. So that final integral on this last page, this last one here, even though it doesn't look that different than the other two, we actually don't have the tools sophisticated enough to integrate that. It does turn out that we might be able to integrate that, but it should be noted that there are some expressions that cannot be integrated, that there is no known integral for them, so, or antiderivative. And that's going to wrap it up for the day. Thank you for your time.